Let's have a look at this circle theorems question. Now, this looks a bit frightening, and it certainly contains several of the circle theorems you should now be fairly familiar with. First of all, they want us to calculate ABD, which is this angle up here. So somehow we've got to move the value of 46 across the diagram all the way up to these points here. Well, the first thing to realise is we have two tangents, and those two tangents hit at D and A. Look at this triangle here, formed by those two tangents and the chord between the two meeting points. The lengths of the sides from the common point X to where the tangents graze the circle must be the same length. We've got an isosceles triangle. So therefore, these two angles down here in the triangle ADX are equal. So let's for the moment call them X. So in triangle ADX, I can say that X plus 46 must equal 180 degrees. So therefore, 2x is equal to 180 minus 46. And if we work that out, x is equal to 67 degrees. So we can pop that on the diagram. So our attention now turns to the chord AD, because the angle between that chord and the tangent is, we've just found out, to be 67 degrees. What 2 points does that chord subtend? Well, it subtends point B and point C. And by what I call as the nasty circle theorem, it's the least obvious. The angle between the chord and the tangent and the angle subtended by that chord to the opposite side. The theorem says that both these angles here are 67 degrees. And we've actually got our answer. I know it's a pain to write all that, but you do need to give the examiners proof that you know why you've declared angle ABD to be 67 degrees. So that was part A. Now let's have a look at part B. And they need us to find the angle BDA. Now, the one fact that the question has given us, which is a little bit hidden, and I've not popped it on my diagram, is that these two arrows, the line BA, which in my diagram is here, that line is parallel with this line, which continues up here. So that's now going to spread the 67 somewhere else. Where is a Z? Well, the Z is here, look. Up here, along there, and up here. So the angle in here, which is that, is also 67 degrees. Incidentally, it's another angle between a chord and a tangent. That might come in useful later on. The chord this time being the chord BD. We're just covered in chords everywhere. All these blue lines are in fact chords. But where can that take us to find the angle we do need, which is BDA? BDA is this one here. Okay, so let's write that down as a fact. As the line AB is parallel to the line DX, angle BDY is equal to 67 degrees. So therefore, the angle that we want, which is the angle BDA, must be equal to 180 minus 67 minus 67. And the reason for that is that they all exist on the same straight line. Look, 67 plus our yellow dotted angle, that's the one we want, and another 67. And this turns out to be 46 degrees. So that's the answer to part B. And we can pop that on the diagram. I know the diagram's getting incredibly cluttered, but this is a reason for being very neat with what you change to a diagram, and certainly do it in pencil. If you start popping ink all over it and you get it wrong, it will turn into a complete mess and you won't know what you're doing and you may not be able to finish the question. So that's a big danger. So let's have a look at part C. We're to prove that ABD, this guy here, is isosceles. Well, now that we've got our 46 here, we know that this angle must be 180 minus 67 and 46. Well, actually, it's the same numbers as we've got up here. So I can immediately see, yes, it's true. But let's write something down. So the angle they want us to find is this angle here now. Let's give it a very temporary name of Z. So I can say that Z plus 67 plus 46 must equal 180. And it turns out that if you work that out, that Z must equal 67 degrees. I am really running out of space. Therefore, triangle. What do we want? ABD is isosceles. And that is your answer for part B. Let's pop that on the diagram. So that angle there is also 67 degrees. Okay, part C says, prove that the triangle CDF, that one there, and ABF, oh, it's the two slivers up here. Let me see if I can, it's that triangle there and that triangle there. And they want us to show that they're similar. Well, what do we know about the triangles which are the same? Well, we know that angle and that angle are the same. We also know that that angle and that angle are the same because they are just opposite each other. They're opposite angles in a cross. So we've got angle, 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 angle. Have we got these two angles the same? Well, actually, so as we've got two angles which are the same in a triangle, the third angles must be the same. But you can say that angle BAF equals angle FDC. Well, I'm going to write the circle theorem answer, which is that they are two angles subtended on the chord BC. Therefore, triangles are similar. And that's your answer to part C.